All right, welcome everyone to the last talk in our webinar series, the Laplace's Causal Daemon series on the intersection between Bayesian inference and causal inference. So today's talk is going to be from David Rohde, who's a staff researcher at the Criteo AI Lab here in France. A lot of David's work is around recommender systems and causality. Today he's going to be speaking on causal inference is Bayesian inference. A beautifully simple idea, but not everyone accepts.
Okay, thanks, Mike. And yeah, just in case you didn't hear it, so Mike will take questions from you and read them out, and so put them in the quick Q&A box. And I mean, I can't deny it. I'm going to be a bit controversial. Some of you will disagree with some of the things I'm saying. We can kind of clarify certain elements during it, and if you really strongly disagree at the end, we can sort of hold off some discussion there. So I'm very happy to spend time with talking to people with different perspectives on this. I'm going to give a fairly long prelude here. I wanted to talk a little bit about how this talk came about, and in fact how the whole series came about. And I also want to really give a big thank you to Finn Lattimore, because the fact that I may know something about causal inference is a lot due to her. We started talking together about causal inference a number of years ago. In fact, we were doing quite applied work at the time, but we sat down and sort of realized we had a different perspective on things. And we said, great, that's interesting. Like, let's work through both ways of looking at this. And actually, a number of years later, we attempted to publish a little paper in some conferences where we said, okay, we think that you can actually solve causal problems just using Bayesian inference without using any of the extra tools that are sometimes advertised. Now, we weren't surprised that some people sort of objected to this idea, and they saw it as fundamentally wrong. And we got really very mixed reviews from these papers. We got some reviews of people saying, well, this is really great, we really like it. We got some people saying, actually, that's trivial, it's so obvious, or I knew this already. And we got a few really negative people saying, like, this is absolutely wrong, what are you talking about? This makes no sense, your title is wrong, and you're misleading people. So I mean, this was interesting for us, and I mean, actually, we have some sympathy for the people that say this is boring and there is nothing really, there's nothing really new here. So, but we still sort of wanted to promote the idea, and because we thought it had merit, and the fact that some people thought it was wrong and some people thought it was trivial was in itself interesting. So we organized a little workshop at KDD last year, and Mike was one of the other organizers, and Finn was a speaker there, and we organized a panel discussion, etc. And I actually, greatly to my surprise, I found that perhaps some people that I thought would be automatically on side with our idea actually expressed a very different idea that was more in line of the Pearlian, Judeo-Pearlian line of thinking. So on the basis of this, we organized a panel discussion. We had amazing people involved. It was sort of a really shocking to sort of have that we were able to sort of get a panel discussion with some really impressive people. But I was surprised by some of the perspectives that came out of this. And so after this, I always had this idea, well, I'm having trouble getting this idea out in a published platform. I will share it. I've got access to my own platform here. I'll share it here. And then I thought, okay, well, maybe we can add some other speakers to this. And then we got these incredible speakers, like all four of the speakers, I think you'll all agree, in the schedule were absolutely amazing. And so then I feel slightly sort of embarrassed to follow on with just me at the end of it on this unpublished idea, maybe wrong, maybe trivial. I believe in it, I'm going to fight for it. But that is the story about how I came to speak in the schedule in this place. So the title of the talk is what I'm going to be arguing for, but I'm going to sort of highlight that clearly some very celebrated people do not agree with this. And of course, there's no surprise that Judeo-Pearl will say, well, if I'm remembered for no other contribution except for existing on the causal statistical distinction, I would consider my scientific work worthwhile. Now, of course, Judeo-Pearl is one of the greats. He's a Turing Prize award winner. Michael Jordan said he was one of the greatest AI researchers of all time, or perhaps the greatest. There's no argument with this, but I mean, I consider this a very crisp statement, which is useful, and it's a crisp statement that I will disagree with. We had the great pleasure of having Carlos participating in our panel discussion, and he made, again, this very succinct statement that I'm going to argue against. Statistical inference is, I have a sample now, and I want to make inference about the distribution. The causal inference part is making inference across distributions. Okay, very clear, and I'm going to explain why I don't agree with this. Again, I wasn't particularly shocked. I mean, of course, all of these are amazing researchers, that goes without saying. But again, I wasn't particularly shocked that Larry Wasserman was both very clear and didn't agree with my position. And here he says, okay, I have a data from a distribution, I have a causal question. Task one for me is, can I express the causal question as a function of the distribution? To me, step one is clearly write down the causal question as a function of the distribution, independent of how I'm going to do inference. And again, he repeats it with essentially the same idea. This, to me, is a maths question. It has got nothing to do with statistics. Once I have done that, I can ask the question of how I'm going to estimate it. I can estimate with Bayes, or I can estimate it with frequent inference. But I do think it's important to separate writing the causal effect as a functional and talk separately about how you're going to do the inference. So we're seeing this idea that there is a separation. There's a thing called causal inference. There's a thing called statistical inference. And you could do the statistical inference with Bayes or something else. And this is the way we should be dealing with these problems. It is here that I'm very surprised. And of course, like Philip David is a Bayesian legend. I won't attempt to list his accomplishments. Except that in many things in the foundations of statistics and causality, he's been a great contributor. And to my very great surprise, he appeared to agree with this position. This is maybe not the as succinct a statement, but he's saying, well, actually, there's a complete separation of these causal and inference tasks, and you can do the inference task with Bayes, or as he says, independent of your philosophical point of view. What is everybody talking about here? So this is causal inference as per the Pearlian view. Larry, I get to call everyone by first names now they organize a webinar. No, I don't know these people very well, even if I'm happy to mix with them on virtually. He corrected me and said, look, some of these ideas have older origins with Robbins, etc. I'm not going to do the history justice, but I'll mention that there are many people involved in this. This is the Pearlian perspective of what's going on, and a Pearlian graph. A very standard graph is that we will start with Z like this, and then we'll have an arrow going out of the Z to the T and the Y, and then the T. So we're going to call the Z a covariate, the T a treatment, and the Y the outcome like this. And we have arrows like so. And if I think this is actually hard to understand, so I've written it with Python pseudocode that tells you sort of what's going on here, where we have a parameter. We're going to sample from a discrete distribution here with Z theta. We sample our Z. Now that we have the Z, because we're going to follow the arrows, we can now sample the T conditional on the theta. So we're going to index T theta with Z and get our T. And then finally, because there's two arrows going into the Y, we have two indexes here, Z and T, and we're going to sample like this. And we can sample from this many, many times. And of course, if we were to do this, we've got the joint distribution of all these things. And in fact, we could estimate all of these parameters here. Now, the causal inference part, as per this perspective, is to say, well, here's a new function. We can represent it as a new graph. The arrow between the Z and the T is now gone. What happens if we set the T as we want? It's becoming an argument of the function here. And can we predict how this function is going to behave for given inputs of T? Now, the do calculus says, actually, yes, we can. We do the estimation of all of these parts here, and we can compute it as this integral like this. Okay? And that is what causal inference is. It gets harder, and so there's many graphs here. I'm just showing a couple and actually these are very standard ones that come up all the time. So this one is, okay, the only difference is we've made the Z transparent. So it means that's latent and we don't get to observe this. In terms of the Python or the Python pseudocode, we no longer see the sample of Z. So we can run this many, many times, and we can of course get a joint distribution on T and Y. but we will never know the parameters here. We won't know Z theta for sure. And actually, as a consequence, becomes impossible to know what the output of this is going to look like given infinite rows of this one. So these are the types of questions that the Pearl calculus and the Pearlian approach answers. So now I'm going to this is sort of almost the end of my debrief, but if a really strict Bayesian, I hope Andrew Gelman wouldn't call them crazy Bayesians, because I think there's something in this perspective, De Finetti famously opened his 2-volume treatise called Probability of Theory with the statement, probability does not exist. And with this sort of very interesting, colorful expressions, he says, well, I think this is a misleading path to try and talk about estimation of probabilities. Now, I'm going to explain in some detail why he would do this, but this is like a teaser for the rest of the talk, and just to say, well, everybody has said that causal inference is about how I'm going to turn this into this. And De Finetti has just denied the existence of this thing that you're going to transform. So from this point of view, I mean, maybe you would still say, well, this is a good methodology. But I think the idea that you can just say, well, you can use Bayes to do this estimation and then use something else here, at least if you're adopting this fundamental view of De Finetti, cannot be done. So do we have a question, Mike?
Actually, I have a question, Dave. If you can you, and I don't want to go off on a tangent, but can you explain a bit behind why De Finetti said that? And then the previous quote, like what's the reason?
I think the best is to wait to see how good a job I do of it in part 1. Because I'm going to try to explain that, because I think it's important to understand this, and then we can see if there are more questions.
Okay, fair enough.
So that's my teaser for a fairly long teaser, but I'm going to talk about why there are these 2 views of probability. One of them that says that probability is a decision theoretic primitive and can be used, we can think about betting on horses and things like this. And the other one is probability applied to statistical problems. And there's like this two-pronged view of probability. Now I'm going to kind of use the tools from this to try to argue that actually causal inference is just inference, and we need to put these 2 things together. And then finally, I'm going to sort of summarize this. But I'm going to go a little bit back to the basics that maybe we all studied but forgot about, and to try to unify some of these ideas a little bit. So. Okay, so probability as a decision theoretic primitive. How does this work? I'm also going to mangle the history a little bit just to make the narrative a little bit stronger. Sorry, I shouldn't look at the chat. So yeah, I'll mangle the history a little bit, but it's usually agreed that Frank Ramsey was the first person to axiomize decision-making under uncertainty and to present this argument. It's mangled in the sense that the Dutch book argument is usually attributed to De Finetti. But what we're interested in here is probability as a decision theoretic primitive. And so we can have any event whatsoever. It could be that Russia will invade Ukraine. It could be anything like anything so long as it's verifiable and that you are able to bet upon it. And then, okay, we can define probability here, saying a person saying their probability for P of X equals 0.4 for an event X equals X implies they are different to these 2 possibilities. One is receiving 40 cents, and the other one is receiving $1 if it turns out X equals X and 0 otherwise. There are assumptions baked into this, of course. We can provide a little operation. There's something that's called the operational perspective. We can provide an operation for measuring this, which is we can start off by saying, well, would you prefer 50 cents or $1 if it rains tomorrow or 0 otherwise? And implicitly on the second one, you're computing an expectation. You're saying, well, actually, when I think about it, I'd prefer the 50 cents to the $1 if it rains tomorrow and 0 otherwise. Now, we can go to the other side and say, well, would you prefer 30 cents? And this is a less attractive offer now, of course, because it's less, or $1 if it rains tomorrow and 0 otherwise. And here you would say, well, actually, my expectation is they will get more money on it. I'm tempted to say on average. It's not on average. There's only one realization of this. $1 if it rains tomorrow and 0 otherwise. So in expectation, my expected utility, even though this only occurs once, is that I prefer the second. And at that point, we've bounded it, and we might at some point find a point where actually, you're indifferent around this area. Now, of course, you can attack this argument, and philosophers do. The most general case is that we can have, well, not most general, a more general case, let's just say we have three things, X, Y, and Z, but it can be as many as you want. It equals P. It implies an difference between P dollars and $1 if X equals X, Y equals Y, Z equals Z, and 0 otherwise. So it's $1 if the event happens at 0 otherwise. And following this argument, and you see that these numbers, these P's, are indeed probabilities. They are between 0 and 1. Certainty is represented by 1. Probabilities of exclusive events add. We condition by Bayes' rule, and yes, there are some caveats. And in the literature, they sometimes even use the expression money pump. The idea here is that you can create a Dutch book by making systems of bets that could exploit any inconsistency. And I think we all have an intuition that bookmakers have some consistency properties that they must satisfy, that the odds are related to probabilities. So a few things to highlight. There's only one realization of X equals X, Y equals Y, or Z equals Z. So it happens once only. This is, I think, we're going to come to it, but it's like if there's only one happening, probability is not a phenomenon outside. Probably does not arise out of frequency, and it does not arise out of symmetry. It is operational. I gave a procedure for measuring it, but it's personal. It's for individuals. It's really important that events must be well defined, that we can agree that the event happened or it did not. It is subjective, and that makes it a decision theoretic primitive. If you satisfy all the axioms, you can actually yield subjective outputs because you've given subjective inputs, and subjective outputs let you order decisions. So that's strong. This is something that pragmatic people, which sometimes I try to be, would say, well, this only applies in a closed world. But I think it's a powerful argument in the domain it applies to. The operational part of this and the operational subjective, I think we need to take both seriously and not seriously. And one reason it's hard to take seriously is the space of X, Y, Z could be huge. If I flip a coin 10 times, there are 2 to the 10 sequences of things that could happen. You enumerate the entire state space and put probabilities on all of them under this approach. And there's other technical things that I'm not going to go into, but you can, some people don't like this argument and they attack various aspects. The linearity of utility is a bit of a problem here. That's definitely a real problem. Sometimes people say, and it's not, there's an argument here that separating probability and decision-making is difficult, and that's a fundamental aspect of this approach. But I'm going to kind of skate over this. If you disagree strongly with this, then you probably won't find the rest of the presentation very compelling, but you may not be here, I don't know. I'm going to make a little brief comments on operationalism. So, and I'm going to do this with reference to causality examples because often there are actually lots of terrible ones in the literature. So I actually think ones around medicine are great. So did the drug cause the patient to recover? Does the vaccine prevent symptomatic COVID? Also, if you're running a recommender system, as we do at Criteo, you may be interested, did the recommender system cause an increase in revenue or some other verifiable metric? And if you can formulate a bet, specifically if you have a treatment and control group, then you're likely in a good space. Why mention this? Because actually causality literature is filled with not great examples. I tend to think that people do this to make presentations that are fun, and I like presentations to be fun. Like in economics literature, you sometimes see, do Christmas cards cause Christmas? This might be great for sort of illustrating the differences between correlation and causation, but what does cause Christmas even mean? The wet pavement caused me to break my leg. You see sprinkler type examples in Bayesian network situations. For me, maybe I want to be really explicit about this, and it might narrow the scope of what I'm talking about with causality in a way people don't love. But for me, if you're talking about causality, you have a decision set that you optimize over, and there are outcomes that you don't know that will occur. So there will be optimization over the decision set. It means, for example, though, that physics, astronomy, etc., there is no causality if you're not selecting decisions, and you're not intervening like this. I don't think, from the same idea, I don't think immutable attributes, because they can't be changed, I don't think it makes sense to think of them as causes of things. Again, there's a really wonderful talk by David Blyish and Wang on the revenue of film and how it's caused by the actors in it. Lots of jokes about James Bond and Moneypenny. It's probably fine for the purposes that use it, but I think analogies break down, and I think I prefer RCT or like really verifiable examples. So, okay, so here at this stage we've axiomatized decision making under uncertainty. We have, but how are we going to start talking about statistical problems? I'm going to move closer to Mike's question: why did Definity say such a thing? So right back in 1926, this is a quote from Ramsey's paper that says, okay, the differences have been between statisticians who for the most part adopt the frequency theory of probability and logicians who mostly reject it, renders it likely that the two schools are really discussing different things. And the word probability is used by logicians in one sense and statisticians in the other. And then referring to statistical issues, he says, for all this, see Fisher. And I mean, this is sometimes brought up because Fisher is sometimes like a Bayesian villain as well. So Ramsey is actually saying, okay, well, I've got my theory that tells you how like bookmakers can set odds and this sort of thing. But for the statistical stuff, which Pearl and others were saying is something we modify and transform to do causal inference, that's a different thing that's out there in the real world, and it's just a different phenomena, and the probability can be used differently in these two places. This all changed with Definity, who actually in the 30s, the year 75 is the translation. So just shortly after and independently says, one cannot admit that the concept of probability has an objective value. Why did he say this? So here we're going from the Freeform. So this is a nod to Finn, who does great talks using this game in the Incredible Machines. We've got Freeform, like events, the cat, the balloon. We probably are putting high probability that when the balloon busts, the cat runs away. So this joint has, so we can do things with freeform events, whatever they are, so long as we can bet upon them. But with statistics, we actually usually have some notion of something like repeated measures, x1, x2, x3, etc. And actually, I find it's going to be useful to make these individuals. And we can, for example, it could be measuring seroprevalence on individual x1, x2, x3, etc. And so we can actually apply, if you think about it, the original theory, because it's free-form events, there's nothing special here. We could do this, just the space is enormous because it's going to be to the n. And that's going to be a lot of betting questions that we're going to be asking ourselves. But you could do it, at least in theory. If you take the operational to mean to not account for the fact that the size is enormous. But Definity came up and said, oh, well, actually, we're going to introduce exchangeability. And we're going to say, oh, if we can do an experiment n times before we can bet upon them, we can let n equals 2. Okay, now we have 4 possibilities. As before, we can confirm these as prices, points of indifference for each event. We can check they should sum to 1, and etc. All these sorts of nice properties. But we might additionally assume exchangeability, which here it says, okay, there's actually for me no difference between x1 and x2, but they're not independent. I am willing to learn about x2 if I see x1. So there is some dependency. If it was independent, it would mean that viewing x1 told me nothing about x2. But we do have an exchangeability, and that means that I'm in invariant order. So I'm going to give the same probability to x1 equals 0 and x2 equals 1, and x1 equals 1 and x2 equals 0. Of course, this is a trivial example with only 2, length 2, but if we consider a longer sequence of length n, we drop from 2 to the n to n plus 1. And that's because, flip a coin n times, you can get anything from 0 to n heads, and so you get n plus 1 states. So we could again do a point of indifference to each of these things. But what we find actually with this really celebrated result, once you make a small technical, there is another technical thing that is important to include, and you wouldn't typically want to include. You can represent sequences with this exchangeability property using this representation here. And in fact, it looks like probability theory, where we're getting the usual Bayesian thing that some people actually historically really objected to, where we've got h of theta being a probability distribution of the parameters, and we've got this thing that looks like the likelihood here. When we have two states, we can write it like this, and we can even reduce it to sufficient statistics, the number of successes and the number of fails. So moving on, like another thing that flows from this is that once we've made all of the assumptions, and perhaps you and me have different subjective probabilities, but we agree on this exchangeability property. So that means that you and me will have different h of thetas, but we're agreeing on this part here. So we can look at this part here and see what it does. And I mean, I think there's a function many of us are very familiar with. It's a likelihood function of a Bernoulli process, and it peaks sharply on the frequency of S on S plus F. So it peaks sharply on the frequency, and as you make S and F larger, as you have a bigger sample, the likelihood peaks very sharply indeed. And so you and me will be in agreement, even if we have different h thetas, so long as they're not zero around this region, that the likelihood spikes. So here we get a Bayesian law of large numbers. So we can also make okay, this is only giving you the agreement between probability and frequency. To talk about causality, we now need to obviously talk about having an outcome and a treatment. So I'm moving sort of slowly towards this, and I'm going to say, okay, well, let's give the outcome 2 states, the treatment 2 states. So it's a four state scenario. And for a reason that will become clear very soon, I'm going to parameterize it with 2 parameters, but you can see they're always doing the same thing. The beta and the theta are everywhere. And we have y comma t, and again, we get our law of large numbers. We can exchange any row and column, not any row, like we can flip the row T2 and T3. We can't do anything with columns. I shouldn't have said that. And we can write out the difficulty representation theorem like this. Of course, it can go as long as you want. And we get a law of large numbers, this time with 4 states. We can look at the frequency of the 4 states and make a predictive distribution like this. So this is useful for doing more standard statistical inference. We can fill in missing elements, be they like a new element y and t, or if we can do something that's more or less regression. We know y1 to y5, what t1 to t6, we can fill in y6, etc. We can also, by the product rule, refactor this into y given t and p of t given y given t in the parameters beta and theta, and t given the parameters beta and theta. Okay, so this almost looks like regression, but it's not. And so now I'm going to talk actually what happens when we go from the regression assumption. So currently we have the combination of beta and theta in both places. So we have y given t and beta and theta, t given beta and theta. And this is actually following very closely into parts of Fan Lee's presentation. We're going to change it from y given t with only the beta and t given only the theta. And in terms of exchangeability, actually, we have kind of the same results. So there's a lot that's similar between these, and we can flip any pair. So here we flip the 7 and the 4, etc. You can do this. So I'm giving a data set here that's making it a little bit clear, because this is the new record that you're going to be predicting. So I'm just thinking about the exchangeability in the new record and all the old data set, but there's many more exchangeabilities that are possible. And this also applies when we have this restricted formulation here. It's also the case that the joint distribution of any individual y and t is unconstrained here. So there's a lot that seems common about these two things. So we could ask, have we done anything by removing the theta and the beta here and restricting the form like this? And in fact, we have. And there are a few things that allow you to see this. So one is that something that we talk about sometimes in machine learning is semi-supervised learning. So semi-supervised learning is, I'm going to say, well, I'm interested in using the t's to predict the y's. But I don't have that many pairs of y and t, but I might have a lot of pairs of t. Sorry, a lot of individual t's. And so is this going to help us? And under this model below here, we see actually it does not help us. Why is that? Because we get lots of t's here. These will combine on the likelihood for the theta, and so the likelihood on theta will sharpen considerably by the use of all these additional t's. But what we need to go from a t to a y is information about beta, and it provides none. So under this model, having additional t's does not help you predict a y given a t. The other thing which is actually a very powerful and important reduction, is that if you make these assumptions, then it actually becomes unnecessary when you're doing regression to even specify this part of the model here. So as I mentioned before, when you're doing regression, it can be thought of in this perspective as, I don't know the y7 here, or the yn, but I know all of these y's here, and I know all these t's plus one more, and I want to fill in this missing element here. And you can see again, it's irrelevant how you specify the model on this and the prior on this. You only need to worry about this piece and this piece to do this prediction. So this is obviously a powerful restriction, but it's a restriction. It's not an assumption that always holds. And so the top is indeed more general than the bottom. We can also draw the idea with a graphical model in this case. And so this is just showing a probabilistic graphical model where we have the plate represents the product symbol here, and we have an additional t coming out like this. Okay. So this is all the background. And now I'm going to make the case that causal inference is just inference. I'm going to make it in the very general case, and sometimes I think when people want to be very general, they can actually be quite vacuous. And so my general case will be pretty vacuous, but it will just simply make the case that it won't use any exchangeability, which will mean it's different for people with different views to be brought into consensus, but it shows how the basic reasoning is still sound. So yeah, we're going to use, if you like, the Ramsey version without the exchangeability extensions due to Definetti, and which also means we have the most general type of data. So if D is the data, it could be something that's biologically plausible. It doesn't necessarily need to be a randomized control trial, but it also means that the data we're open to the data being irrelevant or very low quality. We're also going to set some T star, be a treatment that's applied to a new unit in the future. And Y star will be the response to the treatment. So maybe T star is we give the drug or the placebo, and Y star is does the patient recover. So we want to use D to inform us about how the response Y star changes when T star changes. Well, the most general algorithm is actually extremely simple. You specify a joint distribution using the operational method described at the start. And you can kind of laugh at me if D is of large size because the number of bets is enormous, but the algorithm still holds. That we specify a joint distribution like this, and then we condition, and that's it. And this really has to hold because we're sitting on unless you dismiss the axiomization of decision-making understanding, it really must hold. So it's really your only choice to fight this argument, I think. Anyway, like I can talk about parts of it. The criticisms I think are reasonable and not so reasonable later if someone has questions. But importantly, and in contrast to what was said at the start, all assumptions, be they causal or not, are encoded with probability theory, and the causal inference part uses nothing but conditional probability. So, yeah. So, sorry, I don't know if the comments are interesting to bring up, Mike. I'm happy to take them, but anyway, I'm moving forward. So maybe we can say a few other things, and these are moderately trivial because the case is so general that you can't say very much other than use probability theory. But we can say that the marginal in D is unaffected by the treatment, and this is just temporarily. So the general factorization would say you can have this conditioning on the T, but the D was collected before we did the treatment and is to another unit. So we think we can reasonably say this. And how do we think about this? Actually, one way to think about it is I have a joint distribution on my Y star, my D, and I'm going to think about this when I set T star to be the first treatment, and then I'll have exactly the same process that I'm going to run again with T star set to the second treatment. And then I just do the conditioning twice, once for each of the joints. The marginal of the D, of course, is common, but the way the Y star is related to the T star might might well differ. Okay, of course, that's fairly vacuous. Because the scale of what you're going to do is so large, but I think it's also the logic that people are using when they're not using RCT data. Typically, they're using mechanistic design. I think it's this sort of thing. So I'm going to go to an exchangeable model now, and I'm actually going to jump straight to the sort of the model that we hope we're in usually when we run an RCT or trying to draw causal inferences. And this makes quite strong assumptions. So the D, now I'm going to view it as lots of pairs of Y's and T's. So with N repeats, so Y1 to N, T1 to N, and we're going to have the new Y star that we set here, and given the T star. Maybe something I didn't mention enough is that the treatment that you're thinking about to set in the future has no distribution. And actually, when you're doing the manipulations, you'll do probabilistic things on everything here, conditioning and marginalizations. But the T star you're going to do optimization for. Usually, you're going to try and set T star to produce a desired outcome in Y star, whatever that may be. So you'll do decision theory later on. So we need a joint distribution on this whole thing here. And it turns out that if we use this type of factorization here, which implies a certain partial exchangeability structure, that things work very nicely. So let me explain how that works. Here again, we've got this very small data set of 6 points and Y star, T star. Now, if we made the exchangeability assumptions as before, so we have all the exchangeability as before. We can flip any row as you want. But we have another one, and this is that if T star is set to 0, that means that we can flip this Y star with any other point where the T is set to 0. So we have T3 equals 0, and we can do an exchangeability here where we're flipping the Y star and the 0, etc. We also have T6 equals 0, so we can flip here. Again, the same argument applies to 1, so we can flip with it to any 1 like this. So there's a special exchangeability assumption that we're seeing. There's again, none of this is, you could argue none of this is new. Lindley makes an argument similar to this, but I find not particularly clearly. I'm trying to express it more clearly because I think it has more merit than maybe it's been given. So long as you make these types of assumptions, you can make these sort of inferences, and it's almost this case that you can say you can separate these things out, but sort of as per Andrew Gelman's talk, you might do something hierarchical and, for example, pull the treatments together, etc. But anyway, that's not the subject here. What happens if we use the more general model? So I'm going again. What's going on here is we've got y given t comma beta and t given theta. Now I'm putting in both parameters here, beta and theta, beta and theta, beta and theta. Well, you can't say anything anymore, actually. Once you've set the T star here, you can't say anything much about the Y star. What I'm saying is you can't say anything is of course, if you specify all the details of this model and condition, you will get conclusions. You will get a predictive distribution on your T star of Y star given T star and all the data. So you will be able to compute this, but you will likely see a few things. Firstly, that you will have a lot of variance on it, and like it could really, really be a lot. The other thing is that if I do my inference with my priors and you do the inference with your priors, you'll likely draw different conclusions. So you'll get a warning that this isn't a good idea in that sense. And another way you could look at it is you also see that maybe you and me do both condition on it with our different priors, but we both could agree that there would be great utility in generating good data where we like a RCT data where we would be brought into consensus. So we might disagree on Y star given T star and data, but we may agree that running an RCT is of great value. So, okay, here we only have Y and T. I'm going to talk a little bit more about what happens when you add in a covariate. So this nasty case that I just mentioned, in the Perlian world, you usually create it by adding in what they call an unobserved confounder. In the Bayesian world, it's often called a latent variable. And actually, this is just another way of creating this. And there's actually a really nice almost symmetry here, where with Definetti, what you do is you create you use unobserved random variables with products, and the unobserved random variable sits outside the product like this, and it invokes exchangeability, and it makes things nice typically. In the Pearlian world, what you do is you will typically put your unobserved latent variable within the plate, and it breaks exchangeability and makes things harder. So there's actually like they're almost used in opposite senses here. So these are both ways of representing this difficult case. We also have, in terms of famous cases, we can, if you start to make the Z observed, you get one of the classic cases of Simpsons Paradox. And if you here, we've got the arrow reversed, and you get the other case. And this graphical demonstration, it kind of quickly gives you like the intuition of the two of them. So in this case, and the way it's usually brought up is we see the data as per the left. So the color should be viewed as the Z, the T, and the T, the treatment, the Y, the outcome. So in the left, it looks like sort of if we condition on the Z, we can sort of see two lines and say, well, as we increase the T, the Y increases. But if we draw the other graph and use this model here, we can say, well, as the T increases, the Y decreases. And so how can this be resolved? Well, you need to decide, are you making these types of assumptions, or are you making these types of assumptions? In my paper with Finn, we also covered the front door rule, which is actually a lot more complicated. It has an unobserved latent variable like here, but it actually turns out, and to the surprise of many people, if you put in a variable here that isn't affected by the unobserved latent variable, then you can actually identify things. And so you can draw a consensus of inference. And in some sense, the main result of our papers, we show that probability theory generates that result just fine, just like the do calculus. Returning to the Simpsons Paradox example here, there are slightly different exchangeability assumptions being made here. So they both have this same pattern here with, just jumping between the two, they both have the same pattern here with the Y having the T and the Z going having arrows going into them. And so this can be represented as if we have the T and the Z set to common things. So in this case, let's say if the T star and the Z star are 1 and 0, then we can exchange that Y star with any type place where these are the same. So we can say that's the case here with T2, and it's also the case here with T5, Z5, both of this 1, 0 pattern. So we can flip the Y like this, and that's common in both. But the second assumption is not common, and that is that here if we set the Z star to be something common, in this case, let's say 0, then we can find any other place where the Z is 0, and we can flip both the Y and the T like this. So there's a difference in exchangeability. I'm not saying this is exhaustive. I'm just saying there are different assumptions here that can be understood. This is slightly different in this case because here it's when we set the T star to be common, we can flip both the Y and the Z like this. So here we can flip that with, for example, with T1 is also 0. So we can do an exchange like this. Now, what we're doing here is there's only one realization of the system, and this type of specification can only be done by putting a probability over the whole system like this. But you can sort of see that the exchangeability and this interrogation of this full joint distribution does actually reveal that there are different situations here. So the main results in our paper are sort of these following that we found in all three cases here, we got the same results. So the Pearlian approach is that we have this stochastic system here. If you're going to be a true subjective, you might say this is an externalized stochastic system because we don't necessarily believe that the universe is stochastic. It's something that's speculative. But we have these things generated, and we can sort of answer the question, well, what happens when we mutilate? Well, in fact, we get the same result if we put a joint over the whole system, just one realization of it. Now we condition, and we get the right result. We get a slightly, here is a different case where the arrow is reversed. The do calculus gives this, and again, we show that you get the same behaviors when you condition over the whole system like this. So conditional probability is holding up, and it ought to. because if the do calculus contradicted conditional probability, it would mean that by the axioms of rational behavior underlying Bayesian decision theory, the do calculus had something wrong with it. So it's comforting that the do calculus agrees with probability theory to me rather than the reverse. That's me being provocative. Again, I'm happy to hear other views. The front door rule, as I said, is somewhat more complicated, but we worked through the details in the paper. It's complicated with the do calculus, and it's complicated using probability theory. It's surprising and not at all intuitive that this is identifiable. I think the do calculus this discovery of things these things is very interesting, and it's not so easy to using a likelihood approach to see them. At least it isn't for me. Okay, here's a video Finn made, and so try and play it, see if we can play it. I don't know why I can't. Okay, I'm going to skip it. In our paper, we really emphasize the associations with the do calculus and the fact that there is this relationship between this in the first place and this in the second place. And I thought this had great value for exposition, but it meant a number of people said, "Oh, you're really relying on the do calculus for what you're doing and the causal graphs rather than the joint distributions here." So I presented in the opposite way here to show that actually these things have actually more fundamental view. We had a long discussion on Andrew Gelman's blog about 2 years ago. And I mean, it was very flattering to get a little comment from Pearl. And actually something I find quite amusing is that both Diffinetti and Pearl have a very interesting rhetorical flourishes in the way they write. Here, Pearl is talking about Cinderella's hair color. I mean, and I don't want to sort of diminish any differences between what I'm saying and what Pearl's saying, but he isn't entirely negative either. And it was nice to get that. And if anyone's interested in that perspective, it might be an interesting thing to read. So I'm just wrapping up now, but I can give some other proposals for causal inference that were also covered in the discussion. So a lot of it seems to focus around very simple things, like can we say like P of Y given do T is Y given T, which is basically saying, are we allowed to regress Y onto T? And in the Pearlian approach, you would say, okay, yes, if we get a T from an arrow from T to Y. Rubin does something I find very cumbersome, which is to use a joint distribution on potential outcomes. And Philip David's criticism, I think, here is that you can't have a joint distribution when you can only observe one side of it. To me, is very sound. And to be fair, Rubin seems to at least acknowledge this. David's non-stochastic regime indicator, I think, is slight improvement here, but I suppose I find the whole idea that we're going to go back to the frequency here somewhat backward. Full Bayes, in my view, applies in much greater generality. We just specify this joint distribution and condition, and it doesn't matter if any of these things apply or not, we're getting the right result. Something that can be misunderstood is people might think that I'm saying causal inference is easy, or that I'm giving you the recipe to unlock how to draw causal conclusions from your non-RCT data. And I'm not meaning to say that. What I'm meaning to say is the rules are simple. This is just a Bayesian view. If you're a Bayesian, you typically view rules are simple and modeling is hard, and decision theory is hard. And so I view this as hard because specifying that is hard. And when you see, say, epidemiologists argue like crazy, as we all have for 2 years, it's usually they're disagreeing on an exchangeability assumption, in fact. So a lot of this to me centers around the idea that we have this like regression model. We're trying to predict yn plus 1, but the real causal system is this joint over T star, which will never have a distribution, and the Y star. And it might well be that the relationship between this and this is complicated. And maybe something to highlight is that anything going on within the plate is like more or less the realm of normal Bayesian statistics. And we have exchangeability that will wash out, at least if we do poor modeling badly somewhere, that, but this branching to the Y star is much more of this freeform decision theoretic stuff, like much more the horse racing of Ramsey rather than the exchangeability of the phonetic. But I just don't think yn+1 is null star. I think it's just a mistake to associate these as the same things. So this is actually my last slide, and I'm going to be as direct in my beliefs as I can be, because I think clarity is important. And if people disagree, I'm very happy to engage with alternative arguments. And if anyone would like to present here, this is something we can certainly discuss. But causal assumptions can be encoded with probability theory. I think this is, I've shown this is clearly the case. Causal inference can be done with probabilistic conditioning. And in fact, to reject these first two would be to really reject the fundamental axioms of Bayesian decision theory. Some people do, of course, but I really think that's where you would need to pick the fight. So from my point of view, suggestions that you can mix Bayes and causal inference are completely at odds with the statement probability doesn't exist. If you are a pure enough Bayesian to say probability doesn't exist, then I don't. And this is maybe why I was surprised by Philip David's position, because he can't be said to not understand this. He's delivered the Definity lecture. And I actually would be quite interested if you would like to clarify his position. But yeah, okay, so this is me just reiterating that causal inference combines statistical assumptions based on exchangeability and these more free-form assumptions that are more decision theoretic in nature, where large N will not wash out any differences. The do calculus is still, of course, interesting. It's an important intellectual achievement. Some of the rules, like the front door rule and M bias, which I didn't cover, are really interesting, and I'm not sure that you would easily identify them without using it. But again, I might have a lacking knowledge of the history. I also think the do calculus is likely usable outside of causality, because it really, I think, covers relationships associated with exchangeability. And I don't think we have done a complete job of integrating all of the results of do calculus into Bayesian and likelihood theory. So at that point, I'm going to draw into a close. I think there are some comments and questions that I can address. If I don't know if Mike, if you want to read something out, or
yeah,
or read. Oh.
Yeah, sure. Thanks for a good talk, Dave. So we can formulate, and just as a reminder, please enter your questions in the Q&A box for everyone in the audience. I think we can formulate some of the comments in the chat window as questions.
In fact, I mean, I might turn on microphones as well if people would like. Obviously, we can respond to comments, but yeah, if okay.
We can start with Kevin Murphy's comment and question.
Yeah.
I'll read what he wrote here, and then maybe Kevin can chime in as well. So Kevin writes, I think the focus of people like Pearl are concerned with level 3 counterfactuals, that is causes of effects, rather than level 2 decision theoretic things, that is effects of causes. The latter, your focus, is indeed just Bayes.
Yeah, I can chime in. I'm basically just agreeing with you, David. I like this talk a lot. I think, but I was very surprised that Phil David disagreed with you, because he more or less, as far as I could tell, said the same thing in his 2015 paper. And then when you get to the counterfactuals, then it's a whole different ballgame, right?
Yeah, I mean, I'm nervous that I'm mischaracterizing what he said, of course, and I also wonder if he was just too nice a guy, because we had a number of people saying, actually, there's, basically like a pluralist. You can be Bayesian and frequentist and then do causal inference. Yeah, so, but on your point about higher level, I'm not sure I understand, actually. Maybe
I'm just talking about Pearl's 3 levels of the 3 levels of his ladder. That's what I meant.
Right.
So you have to hold everything fixed in the twin universe sort of view of counterfactuals, right? You're making assumptions that I don't think you can verify. But this is, even Gelman told us last week or earlier this week, right? He wants to ask why questions, which kind of require this, even if they're hard to verify.
Yeah, I mean, that was definitely an interesting discussion. Yeah, there were questions. Okay, I made a big thing about being operational at the start, and yet I do think there are some questions that I'm not smart enough to make operational that clearly have value. Yeah. The levels of Perl, I don't know if I have a lot to say about it. Yeah, I mean, I'd be actually very happy to have a response to this. I'm going back to Australia for the first time, and so I haven't had a chance to sort of invite dissenting views on this, and I'm sure there are some. So, I mean, if you are one, please speak up. Although it's all, okay, I'm always happy to hear people agree with me as well. But yeah, I mean, I was very surprised in fact that the position I took was controversial, and somewhat I do kind of largely accept it's boring. So it made it maybe understandable that it was hard to publish.
I actually did have one more technical question. I haven't read your paper, but it seemed like from the slides you were showing between the equivalence of do calculus and the Bayesian view in the large sample setting. Like if we think in the large sample setting, essentially the parameters, the posterior collapses to a point, so these become clamped nodes, right? You know the value of the parameters, and that's effectively like cutting arcs in your graph, which is exactly what
so okay, you make a good point, and to me this is again a strength of doing it this way, is you can estimate everything that's in the plate. You can estimate, so you estimate, you've got estimates of all these parameters, and then there is some transform that turns out to converge to this. So in the Perlian world, what you do is you have a joint of these things, and really what they're saying is, with a joint of these things, can I get the conditional that I care about here? And I mean, maybe it's worth highlighting that the strangeness of these rules that are produced, where you're marginalizing out T here and yet conditioning on it here, like there is a genuine strangeness. But yeah, okay, to me, a strength of doing it this way is that if this is not that large, or what is usually Bayesians are interesting cases where like the things in here are very large supports, and then you don't get this intersubjective, the law of large numbers really doesn't have any force. You let things be continuous or have large numbers of states, and then the priors are going to start mattering, even if you're filling in missing data within this block, which is like the normal inference. But then we have this harder thing of how we're going to move outside. And actually, there are things I would say you can't really do with it. You know, again, correct me if you're a Perlian view, but when you're doing causal discovery, it might mean that you have like this is not, you know, you're debating which direction these arrows go, and so you could actually do Bayesian inference. You can deal with a finite sample, the fact that you don't even know the graph, and do causality all in one step, all using conditional probability and nothing more. And in this case, you'll get mixtures with the arrows being reversed in this block. And you can't really do that. Like from the Perlian approach, you first estimate, then you do causal discovery, then you do your causal inference, all the separate steps. And to be honest, I'm fairly skeptical about this being practically useful. I think if you're in a world where you really don't know your graph, this is going to be difficult. Maybe cases where I think the Perlian approach would be hard to apply, but we really need to do it is, you know, what if you're using surrogate endpoints? Your Y is something like symptomatic COVID, but you really care about hospitalization and death. Then I don't know what you would do within the Perlian approach. Or maybe you have an RCT, one stratified by age and one by gender, and you have a patient in front of you that you know both the age and the gender of. Then I think the Perlian approach is very difficult to apply in these sorts of scenarios. Okay, I've been provocative, but maybe everyone's too nice to. Okay, there's another comment actually, isn't there?
Yeah, from Pietro Vicia. So he writes, on freeform events, Cox has shown that one can build a perfectly coherent system for freeform propositions that is formally equivalent to the Kolmogorov axioms. There's a discussion about that also in Jane's book. So I think restricting to repeated events may not be strictly needed. What do you think about that?
I haven't written a book about. Maybe Kevin has more to say about this than me. I think I mean, I haven't really read Cox's papers. I just know that Jaynes loves them. But this has got like somehow a connection to subjective versus objective Bayesianism, because the Cox axioms are preferred by the objective Bayesians, I think, and the coherence argument is more through the subjective Bayesians. I like decision theoretic outputs. I want to be able to say I prefer A to B, and I think the Cox axioms are less relevant here. But both arguments apply to single realizations of the system rather than repetition. So both of them apply in that case. Maybe that's more where the question was coming from. Would you like to speak? In fact, I'm trying to find, sorry. Cool. Are there any more? Well, feel free to,
What?
Pietro, feel free to talk later. Yeah.
Yeah, go ahead, Pietro, if you have something.
Okay.
And while we're waiting, I'll hear the question of my own. So clearly there's an elegance, right, to the approach you're advocating. What's aside from that some people might say it's boring, as you said, but what's the kind of the primary objection you encountered?
Okay, well, I think the argument that Paul makes is perfectly correct if you're thinking about frequentist probability. Like, I think it's perfectly correct that you can't do causality with frequentist probability. So I think it's just people not understanding that that's not what's happened. That's not what I'm talking about. And these types of factorizations and the differences between them can only be specified. Like, let's not even think about causality. Let's think about semi-supervised learning. If semi-supervised learning is possible or not is only something that we cannot, it's a joint over the whole data set that tells you this. And so if we're thinking only in terms of frequentist probability, because, and I'm not even, there are more, I think it's just viewing it through frequentist probability. I suppose that's why I think people strongly disagree with it. And I mean, Pearl's made very strong statements on it. Maybe there's a couple of comments I should make, because people have pointed this out to me, and as I said, I could know parts of the literature better. It's possible early Pearl agreed with us more than later Pearl. I, again, don't know the history that well, but early Pearl produced something very similar to this, which he called twin networks, but he was talking about counterfactuals. I'm kind of quite careful to say, well, here's my data, I'm intervening, and here's an outcome. He was more about like what would have happened if something else happened. And I basically agree with Philip David that that's better avoided, even if I like some of the Rubenesque language. Some of the Rubenesque language using counterfactuals is in fact fantastic in advertising, but I think it's sort of something we should not rely on for foundations.
Okay, thanks. Let's see. We have one question in the Q&A box, but it's from earlier in the talk.
Yeah, I mean, I saw that on the way and I didn't. Is this not better referred to as generalizability? Let's turn on the mic. But could you please clarify? I don't understand that one. Are there any more?
Yeah, David. So I was making that comment at the point where you I think you were close to discuss how causal can be generalized and applied in different contexts. I would like to bring in something which has a practical aspect. Can you hear me, by the way?
Yes, I hear you fine.
Okay, so you have data. You're going to build a predictive model. You have a holdout set, and you're going to validate the model. In the validation set, you would like to keep some structure that would enhance the value of the validation. Seems to me like what you are referring to with the exchangeability properties can open up options for cross-validation in a way that would enhance the value of the holdout set as a validation set. I don't know if it makes sense.
You're saying, can this help? Can this theory help?
Right. Yes.
I don't know. I don't know how to answer. When we have the validation set is best at checking of, like, you've got everything in the plate, your observation, you remove some of the elements and you check if you can predict them correctly or not. That is more or less what you're doing with the validation. So that's good. It's far harder to check if you're making the assumptions that bridge between, like, this graph and the causal.
No. It's beyond that. If there is a structure in the data, there is a hierarchy in the data, and you ignore it when you pick up the validation set, your validation is not going to prove very effective. So it's beyond that. It's beyond what you mentioned.
I'm sorry, I don't understand. I mean, I think, yeah, maybe you could ask it again, or or we can take it offline.
You have data with some structure. If you ignore that structure in picking up the validation set, so you just randomly pick up a subset, when you're going to do the validation, that structure will be absent from the validation. And that will impact the value of the validation for your model. So you're going to validate the model with something that doesn't have the structure that was originally in the training set. And I think that what you are referring to could open up an option to induce some structure in the validation set that matches the structure in the training set.
Maybe. Unfortunately, I can't say yes or no, but I mean, it certainly sounds interesting. I feel like we should maybe take that one offline. I don't have anything clever to say about it. Is there any more, or should we say thanks?
Looks like that's all for now.
Okay, well, thanks everyone for coming in, your questions. Thanks, Mike.
Yeah, thanks again, everyone. And we'll have the Placidus Demon series starting up again in April, as Dave mentioned earlier. So please join us for that.
Okay, thank you.
All righty. Bye-bye.
Bye. Cheers, Mike.